Our next speaker is totally exciting and really fantastic. She is a particle physicist who works at CERN. I accidentally introduced her to somebody else as saying that she came from the Hadron Collider, but that's kind of like Marilyn Monroe coming out of a cake sort of thing. It's Tara Shears coming out of the Hadron Collider. I am the Higgs boson. All right, but will you please welcome to the stage the fantastic Tara Shears.
Thank you, everyone. So my talk is about particle physics. I'm a particle physicist, and I want to tell you about it. So particle physics is the branch of science that tries to understand the universe, but from the inside out. And because of that, we think that everything in the universe, that's all of you, that's all of your iPhones, your iPads, stars in distant galaxies, you're all made of the same stuff. Not just atoms, but the same building blocks, the same fundamental particles, held together by a few fundamental forces. And we think, if we can identify these and understand their behavior, then we can also understand the behavior of the universe at much larger distance scales than we have in particle physics. Sounds great, doesn't it? We can understand everything with a very simple model. And in this talk, I want to show you that we don't just think this. We don't just dream or imagine this. I want to show you that we know it and we have evidence. And I thought the best way to demonstrate this was to pick an aspect of particle physics tonight for you, and very topically, just subject it to the James Randi test to see if it passes. I'm probably setting myself up for a fall here, but let's try it out. So let me start off with what we know. And then I'm going to pick one part, and then we're going to try out the $1 million challenge on it. So let me start out with what the universe is made of. So everything that we've seen in our experiments is made of the same building blocks, the same fundamental particles, and we've identified 12 different types of these. 6 of a type we call quarks, and 6 of a type called leptons. And these are really, really tiny. They're at least as small compared to an atom as an atom is compared to you. And I say at least because this is the limit of our experimental measurement. These things are so small that we haven't been able to measure any spatial extent for them at all. Now, what holds these together to make the stuff that we see around us is a small number of forces, fundamental forces. I'll zip through these, and then you'll be experts in particle physics. So there's just a few. So the first force is the weak force. It's responsible for radioactive decay, and it affects every single type of matter particle that I've just introduced you to. And we even have a picture for how this force works, and for how any force works at this very small scale. We think this force is conveyed by the action of force-carrying particles between matter particles, and you get the idea of our worldview. It's very particle-centric. The particles in this case are W and Z bosons. That's the weak force. We also have, more familiarly to us, the electromagnetic force. That's driving these lights, the sound system, a lot of what goes on in your houses. It acts on anything with an electrical charge, and that means it affects every charged fundamental particle too. That's communicated by particles, photons, particles of light. And then finally in our picture of particle physics, we have what's called the strong force. Quarks feel the strong force, and this is one of the things that makes a quark different to a lepton. The strong force keeps atomic nuclei stable because it's an attractive force, and it's strong enough to overcome the repulsion between the positively charged protons in the nuclei that would otherwise drive it apart. And this is conveyed by rather wonderfully named particles called gluons, because they stick matter together. That's essentially all you need to understand most of what goes on at the universe at the very small scales of particle physics. I have missed out one very important force, though, that you've already heard about, and that's gravity. Of course, gravity is very important when it comes to the large-scale structure of the universe. Gravity acts on mass. We know that every single fundamental matter particle has mass. We've measured that in our experiments. But gravity is so much weaker than the other forces at the very small distance scales we're used to in particle physics. Gravity is 40 orders of magnitude weaker than the strong force. So if you're making measurements of these very tiny things over very tiny distances, gravity doesn't make much difference to your calculations. And as you heard before, we still don't have a good theory that knows how to treat gravity at these very tiny scales. So for the moment, I'm going to leave it out of our picture. So we have matter, we have forces. There's one more ingredient in the universe, and that's something called the Higgs field. This is an invisible energy field, a type of energy field, present throughout the universe, and we think that as fundamental particles travel through the universe, they interact with this Higgs field around them. And this interaction gives them mass. And the stronger this interaction is, the more mass they get. And this field, too, has a particle associated with it. It wouldn't be particle physics if it didn't have a particle associated with it. It's the Higgs boson, the very famous Higgs boson. So the picture we have here for how this works is that if you're a massless particle, like a photon, you zip through the universe completely unaware of this Higgs field. But if you're a massive particle, like a top quark, your passage through the universe is impeded by your interaction with the Higgs field. It's slowing you down, it's giving you mass. Now, you can't see the Higgs field because it's invisible, but you should be able to see the Higgs boson that's associated with it. It's a fundamental particle that we should be able to momentarily make in our particle accelerators, and then we should see it in our experiments by the characteristic way it decays. Now, matter, stuff, and forces are quite familiar concepts, but the idea of some sort of invisible field that gives you mass, I bet that's not quite so familiar to you. It's quite a complicated concept, and this is the part of particle physics that I want to subject to the James Randi test, because an invisible field that you cannot test should get you thinking about how we can know whether it's there and how we can make any statements about it whatsoever. So it might even, for example, remind you of something like the ether, that was a very erroneous theory that we had in physics about 100 years ago that hypothesized some sort of invisible fluid throughout the universe. Well, I want to show you that the Higgs field is there. So this is what we're going to do to see if we can satisfy James Randi of the existence of this field. I have two criteria for seeing if something exists and if we know it's there. The first thing is that it has to be testable. We have to be able to describe it. If I tell you there's a phenomena out there that you can't see that does something that you can't see either, you're not going to believe me unless I write down a way it works that you can test. The second thing is, apart from making it testable, you have to make it repeatable. So in other words, I want to know that the Higgs is described by the scientific method, but I also want to know if you do see anything that it's not a chance fluctuation. It's really got to be there. And that's what we have to satisfy. Okay, so let's take the first criterion. Is this Higgs testable? Well, it is, because I've given you my pictures for particle physics about how forces stick matter together and about how the Higgs field gives particles mass. And we can encapsulate these pictures into equations using maths. And these equations form our theory of particle physics. Here it is. It's so mathematically elegant and succinct, you can write it on the front of a T-shirt. And if you go to CERN, you can buy the T-shirt and the mouse mat and the baseball cap and the mug. There are many, many retail opportunities for you to own your own theory of the universe. Now, this theory describes to us what sort of fundamental particles we will see in our experiments, how often we will see them, and how they behave. And in that sense, everything I've told you is testable because it's contained in this theory. And what you might not know is that this theory is incredibly successful. It's so successful that we haven't yet made an experimental measurement that disagrees with one of its predictions. And that's why we've given it the name, the standard model of particle physics. Now, the Higgs field is described by a theory which is actually an intimate part of this theory. Because even though the Higgs field was hypothesized back in the 1960s, the theorists who developed the Standard Model realized that they needed to include it in their picture of nature to make all the predictions make sense and to make the whole thing work. So in fact, that part of the Standard Model describes the Higgs, how much energy there is in this invisible energy field, and how the Higgs interacts with matter. It's testable. We have a theory. This lets us predict how the Higgs would behave. It lets us predict under what circumstances we should be able to see the Higgs boson, which is the visible face of the Higgs field. This gives us a route to be able to test this hypothesis. Okay, now how about actually testing it? Now that's a bit more of a problem because it turns out that there's only one facility in the world where you can test this theory. And that's because the Higgs boson is massive, so you need a very energetic facility to be able to make it, even if it's only for sort of momentarily. But it's also produced very rarely, so you need a very intense source of particles to study. And the facility that can do this is the Large Hadron Collider at CERN. It's where I work. It's it is the most exciting particle accelerator in the entire world. You might have heard of it. It's been in the news occasionally. You know it's massive. It occupies a huge, 27-kilometer long circular tunnel, 100 meters under the ground, near Geneva, so it crosses over the French-Swiss border as you go around the circle. Inside the tunnel, you have a continuous stream of very, very strong superconducting magnets that keep our particle beams circulating around this circle, interspersed by radio frequency cavities that accelerate them up to high energies. And when the LHC operates, we have two beams of protons circulating in opposite directions, accelerated up at design spec until these protons are just going at 20 kilometers an hour less than the speed of light. And when that's done, we bring these beams into collision, not once or twice, but 40 million times a second. And it's what goes on in those particle collisions which is the key to this whole facility. Because when our proton beams meet, for a tiny instance of time, in a tiny, tiny area of space, what we're doing is recreating very hot temperatures, last seen naturally in the very early universe. And what's good about that is that matter, at those very hot temperatures, consists only of fundamental particles, not even atoms or elements. This gives us the source of fundamental particles that we can then study. And when I say early, I really do mean early. We're looking at matter as it existed billionths of a second after the Big Bang. And our idea is then that where the proton beams collide, we can build experiments. And our experiments are like gigantic three-dimensional cameras that digitize what happens in a particle collision and takes a snapshot and records it. And then particle physicists like me can take these recorded snapshots and analyze them and look for the fundamental particles that were produced in that collision and study their behavior and match it to our theory. And if what we see matches our theory, it's wonderful because you understand what you're looking at. But if what you see doesn't match your theory, then that's even better because you can't lose. Because that means you're going to make a discovery of something new. And that's how we looked for the Higgs boson. We hadn't seen it before the LHC, so we were looking for an accumulation of something at a particular mass, so we knew it was a particle, but which we hadn't seen before. Now, I told you the Higgs boson was rare and difficult to see, and I want to prove that with these numbers. So I said that at the LHC, our proton beams collide 40 million times a second. And when our beams collide, more than one thing can happen at the time in terms of fundamental particle interactions. About 100 million things can happen per second. Okay, they're probably not all interesting, but about 1 million of them per second are potentially interesting. And this is a problem because you cannot record that much information. Our experiments are huge. They contain about 100 million channels of electronics that you have to read out in a single snapshot. Our bandwidth, our networks that we use to take the data away from the experiments to storage are limited. Our computer storage is limited. We're limited to maybe a few hundred of these collisions per second that we can actually record. But that's okay because we don't see a Higgs very often. A Higgs boson is produced about once every minute. And if you think that separating out something that's produced every minute from the several million things going on every second is a challenge. Well, let me tell you that we can't even see all of these Higgs bosons. They're indistinguishable from background. There are only a few types of signature where we know we can separate the Higgs satisfactorily from the background. These are the observation channels you see down here. You get one of those produced about every 3 hours when the LHC runs. So you see this big pyramid. You need about 1 trillion proton-proton collisions to get one observable Higgs. That's why you need a lot of data to find it. But we're okay because we have a theory, and that lets us know what it's going to look like, and so we can devise a strategy. And so then our problem isn't finding a needle in a haystack, just finding one of them. Our problem is finding more than one and getting the statistical significance that means that we've actually discovered it. It's like a needle stack of needles, if you like. The problem goes up. But as I say, we know what it looks like. We can simulate it. So we can develop strategies to make sure that we always record this information when it arises, and that when we analyze it, we can then separate it from backgrounds. That's the idea. So you might remember before I get onto that, let me underscore the nature of this problem. I've told you that this thing is produced rarely, but looking for it is a tremendous data volume problem. This infographic behind me is from Wired magazine, and it gives us areas of these circles the data volumes produced by various things. So in purple, up here, the big purple circle, that's business email. It's huge. Yellow here is content uploaded to Facebook and so on. LHC is the dark blue circle up there. It's a similar data volume to the number of videos uploaded to YouTube every year. Just to put it in context for you. Now we're looking at something produced very rarely in that data volume. Imagine watching every single video uploaded per year to YouTube in the hope of finding one that you like. That's our search for the Higgs. But at least we get computers to do it, so it saves the boredom. So in 2012, you may remember that CERN held a public seminar where 2 of the experiments at the LHC, ATLAS and CMS, announced their latest findings in the search for the Higgs. And this was a really big deal because we thought that something was happening before then, but we didn't know whether what we were seeing was chance and fluctuation. This was our first time to see if there was really something there. And CERN was so excited that it invited the theorists responsible for the original Higgs prediction to come along because they might be interested by what was found. There's 2 of them in the front here, Englert and Higgs, who got the Nobel Prize in 2013. Well, what was found was sensational because 2 experiments using independent data and independent methods had seen exactly the same thing. They'd seen evidence of a new particle behaving in the same way. So it was a giant leap for science. But perhaps for us, it was really a giant leap for the Standard Model, because the Higgs was predicted by the Standard Model, but we'd never found it. This was the last missing piece of the Standard Model picture of the universe, so it was great to find it. Okay, so let's come to specifics now. Did it pass the James Randi test? So I've told you it's testable, and I hope I've shown you that using the Higgs, it can be repeatable, because the Higgs produces a lot of data. Now, the only thing left is the statistical precision by which we see it, by which we know it's not a chance fluctuation. And I had a search on the web for the $1 million challenge and what the statistical level of precision that's necessary for any phenomenon to pass to get the $1 million is. And it's quite difficult to find because this is evaluated on a case-by-case basis. But on one archived website, I found that you had to exceed a chance of 1 in 100,000 of being a fluke. That's quite a tough challenge. In particle physics terms, we give it the name 4.4 sigma. I hope this will become clearer in my next slide. 4.4 sigma. Did the Higgs pass this? Well, both experiments saw it with a precision of 4.9 sigma, so actually we did pass the James Randi test. And had we just thought ahead, we could have entered the $1 million challenge, and we could have got enough money to run the LHC for about 2 months or something with the electricity supply. Okay, so it might have satisfied the $1 million challenge, but yes, but did it pass the particle physics test? Well, we have 2. We have one test called evidence, which is fairly weak. It's just a statement that there's something out there in the data that's new, and you don't think you can explain it with the understanding you already have. And that corresponds to a chance of 1 in 300 that you've been unlucky and your backgrounds have fluctuated to look like a signal to you. That's called 3 sigma. Well, we'd passed that. But in particle physics, we have another more stringent threshold for a discovery, and that's called 5 sigma. That corresponds to a chance of 1 in 1.7 million that the universe was mean to you. And if you go back to that seminar and you listen to the talks, you'll realize that no one ever says discovery. So Atlas and CMS physicists present all the evidence, but they're very careful not to say that they've discovered a new particle. And it's because we were only at 4.9 sigma, a chance of 1 in a million, not 5 sigma. And in fact, we had to analyze all the rest of the data we'd collected in 2012 before we passed that threshold of 5 sigma, and before CERN then admitted that we had in fact discovered a new particle. So yes, now we have passed the particle physics test. But it's really hard, and to demonstrate this, I want to show you one of the discovery channels building up from Atlas. These points are our data Higgs candidates, the colored histogram are our estimated backgrounds, and to make a discovery, you want an accumulation of data where you don't expect a background. And it takes the entire data set up to December 2012 before you have enough significance to think there's something new there. And it's only when you compare this to your prediction of what a Higgs boson would look like if it had that mass, and you see it matches, that this is the sort of thing that gives you evidence for thinking you have a Higgs boson in your data. But there's not many candidates there. And altogether, the LHC has only identified about 2,000 Higgs bosons altogether. It's not very much. And so, although we found a Higgs boson, we're still not sure it's the Higgs boson that we expected in the standard model. And to show you that, I have more proof. This is from the CMS experiment. This experiment has counted the number of times it's seen the Higgs boson in every experimental signature, and it's compared that to the number of times it should have seen it if it was a standard model Higgs. If you see it as often as you expect to, then all of these points should line up at 1. And they pretty much do, but there's quite a lot of imprecision here, a lot of statistical uncertainty shown by the red line. There's a lot of wiggle room, in other words. And although this might look pretty convincing to you that we have a standard model Higgs, in fact, this imprecision is exciting enough to generate about 1,000 papers per year by theoretical physicists. Now, you've already heard from Suksi, and please excuse my awful Finnish pronunciation, that theorists often get it wrong. In this case, 1,000 different theories can't all be right. But what's important is that we have all those different ideas that we can then compare to our data to see which description ultimately wins. So there are many, many different things that we could say about the Higgs. This might be the standard model Higgs. It might be a Higgs boson associated with a deeper theory of nature, like supersymmetry. It might be a Higgs that opens the doors onto a dark sector of the universe and then can explain dark matter. It might even, according to unexplained paranormal phenomena website, it might even destroy the universe. Or at least Stephen Hawking says that. You see what happens when you run out of evidence and you end up in speculation. Well, what's interesting here is that there are degrees of speculation. This doesn't just pop up on paranormal websites. It's in the news, more sensationally. It's even in the informed news, if I can use that to describe scientifically informed. And that's because this is actually a prediction. It comes from a testable theory. And this theory says that we can tell if the universe is stable or not, dependent on 2 parameters. I'll show you this map of stability. So depending on the mass of one of the fundamental matter particles, the top quark, which goes from bottom to top, and the mass of the Higgs boson that goes from left to right, our theory can tell us if the universe is stable and in this green, safe area, or unstable in this horrible red area. But we've measured the top quark mass and the Higgs boson mass, and our measurements are shown by this circle here. And we're in this yellow no man's land of instability. where the universe is probably stable, but we can't be sure. Hence the interest. Now, what we're missing here, apart from evidence, is context. And I've told you that this is a prediction from a theory. But this theory has certain assumptions. This is only correct if the Higgs boson is the standard model version. And to be honest, we don't think that the standard model is going to be a complete description of the particle physics universe, because there are phenomena out there in the universe that it cannot describe. That's point number one. And point number two is that even if it was a standard model Higgs, and we live right here, the effective lifetime of the universe is about 1 trillion years. That's much, much longer than the lifetime of our Earth, our solar system, and our sun. So it might be metastable, but it's not going to affect us. And perhaps that was missing from the news coverage. Okay, so we've seen a Higgs, but we don't know what sort of Higgs it is, because we don't have the evidence yet. And this is great, but it's no way to do science. We need more evidence to move on. We need more evidence to see if we have the standard model Higgs, and we might die in 1 trillion years' time, or if we can say something more about the universe, and perhaps more about dark matter, or so forth. So where do we go here? Well, where we go next is happening right now. We're just starting up for a second data-taking run with the Large Hadron Collider. We've started commissioning with Beam, and we expect, if all goes well, that in about 6 weeks' time, we'll start up our physics collisions again. The LHC has been offline for about 2 years, having a rest and maintenance while we've been trying to finish analyzing the data. We're going to take data this year, next year, and the year after. And this is going to be momentous, because there's something different about this data-taking run of the LHC. What we're doing is we're increasing the energy of the beams. For the first time, we hope to get as near to the design energy as we can, because so far we've only been running at about half design spec. So we're almost going to double our energies. And this is wonderful, because what the LHC is going to do for us is to make us see the universe in a way where we haven't been able to study it before. It's going to bring the universe up close. We can look at it with better precision, greater depth. And of course, we don't know what we're going to see there, because it's research and we've never looked there before. And it could be anything. But we hope it's going to resolve the question I've been telling you about. Beside the higher energies, we're going to have more data. And these two effects added up mean that by the end of this run, at the end of 2017, we should have a data sample that's about 100 times bigger in terms of Higgs bosons than we have already. And that's the evidence we need to investigate the nature of the Higgs. That's the evidence that we're going to sort through to separate out what the correct version of the Higgs is. Standard model, supersymmetric, dark sector, whatever, this will tell us. So it's looking bright. So in conclusion, let me go back to the original question I posed, which is, does the Higgs, and then by extension, because the same arguments can apply to the rest of it, does particle physics obey the James Randi test? And I hope you've seen it. It does, because it's science. And this is the way that science progresses. Thank you. We progress, our knowledge grows if we collect evidence from data and we compare it to theory and hypotheses, and we work out which are wrong, which we can forget about, and which are correct, which are going to guide our understanding and improve it in the future. And this is what's going to happen in the next few years with the LHC. We found a Higgs. This whole scientific method has guided the whole history of our subject. It's enabled us to work out what the fundamental ingredients of matter is. It's enabled us to identify the fundamental forces. It's enabled us to predict the Higgs boson and then identify and find it. Now, we might not know what sort of Higgs boson we found yet, but this evidence is going to let us settle that question for once and for all. And that is wonderful. This will be a huge step forward in our understanding of the subatomic universe. And I really can't wait to see what we're going to find. And you should all reflect that this is the power of critical thinking. This is what science and critical thinking can bring you. It's a really fundamental understanding of the universe. Thank you very much.
Tara Shears, everybody.